Hello, good afternoon everyone. Now we're going to be talking about the science portion. Congratulations for having made it this far into the course. So before we begin, I do want to mention what are the topics we're going to be covering in the HiSET or as well as the GED. So for the science portion, we're going to have life science, earth science, which might include astronomy, so we're just going to put space science, as well as physical science. You may tell me, all of them got science in it, it all sounds the same. Alright, let's translate this to more practical terms. Think of it as being biology, your geology, and your physical science would be like your physics. With your chemistry going kind of like in between here and here. Yeah, because I do want to mention that you don't necessarily have to be a brainiac at math, but you do need to understand being able to look at data. I'm not saying being able to crunch numbers, but to see hey, for an example, we've been seeing a spike in COVID-19 cases that you could correlate. There's more cases happening in a certain part of the state. Okay, well then that would be, what can you infer from that? What does that suggest? That's the kind of relationships that we're going to be using math for in the science portion of the HiSET, or if you take the GED. The GED and the HiSET are going to both have these categories. I just want to mention, explain right here. So we're going to be using math as a fundamental. And then with math, we kind of use physics, which is the application of math. And then we put that into our real world with chemistry, and you're like, what? With chemistry, chemicals don't necessarily have to be liquids. Like my skin, it's made of different chemicals, and I am somewhat solid as well as partially liquid. And then we also have biology here. So for this course, we're going to progress from the life sciences, because that's usually much easier to ease into, whereas physics is something that normally is taught in your junior year of high school. So we're just going to get into that much later. Let's just get comfortable, let's get our feet wet, and just kind of explore this. But this is basically how the different sciences relate to each other. It's not an equilateral triangle, but it gets the point across. So let me just go ahead and also give you the breakdown of how much, what's the concentration of each. So with the HiSET, it's 50% of it would be your life sciences. Also with the HiSET, 21% would be earth sciences, and physical science would be 29%. I don't know why they chose 29 and 21. I would have preferred 20 and 30, but that's just how they did it. Whereas the GED, let me get another color. The GED goes with get this marker to work. GED goes with 40%, 20%, and then 40% over here. So the GED kind of like balances out the importance between the three sciences more. Earth sciences, I mean, it's important knowing like different kind of tectonic plates and certain things about magnetism, but it does shift some more things back into like physics, because you get a lot of it becomes a lot of practical hands-on skills. For example, when I had to change my car battery one time, I wasn't so sure about the polarity, about the battery's negative. Does electricity go from negative to positive, positive to negative? I was really I wasn't so sure how to connect it. I didn't have internet access. Phone had died at the same time as my car battery. But then remembering the principles from my physics class, I did take quite a few physics class, so then I felt comfortable enough to like switch out the battery, and I switched out the battery and my car worked. So that also another example would be based on the principles of physics. You know that in order to, like, let's say that this is a person holding out their arm. So we know, like, this is the point of rotation in a person's arm. Do we want to put pressure here or pressure here if I want to make that person's arm go down? I'm going to put it furthest away over here. That way I get maximum use of my energy. So like, let's say I put my arm out and like it's all, I have a better grip right here from like where the joint is, like his arm or her arm, and I put it here. I don't have to use hardly any force, but I have to put more force right here. So these kind of principles are much more handy for day-to-day life, and that's why they're more emphasized in these for the science exam, because it's part of what are the expectations of an adult or a minor with a high school equivalency diploma. So we will be starting off with our life sciences. And we're gonna just go into the course first. Normally I could try to teach you like, oh, this is like how the questions are phrased and like what we're gonna be doing. But I found that when students are kind of like thrown into like trying to like decipher questions without having like the background knowledge, it really hurts them. It like doubly confuses them. So we're just gonna ease in very softly. And if you've noticed about the playlist, there's like other videos like embedded between my lectures. I did that way it's a lot nicer to like introduce the topic with a nice little animation. That way, you know, it kind of settles you into like the topic. Okay, so the first thing that we're going to cover, and some of you might have already guessed what it was going to be, it's a scientific method. Just put this right over here. Alright, so the scientific method is tried and true. We don't just use this for like hardcore sciences like biology and chemistry. We also use this for like sociology and even psychology. it's really a very good way to determine, hey, is my theory accurate? Is it not? And the fact that it tests itself kind of helps make sure it works in like different conditions. So the main purpose of the scientific method is to investigate events. So like, let's say I see a certain phenomenon. So I see, oh, this pen fell. Okay. I want to know more about that. So then you want to acquire knowledge. So you start off with kind of absorbing. Let's use a different color for that. So we observe it, we see it happen. And now we have questions. So we develop a question. What do we want to know? Now, it's very important that the question is measurable. This is true also with like sociology and like psychology. You have to be able to measure. You might not be able to like measure it numerically, in the sense of like, well, with this sort of medication, we have a 48% decrease in 48% decrease in like patient symptoms in the first 5 days, blah blah blah. You can also say it could be like for like a psychology study, patients after like cognitive behavioral therapy, which is just like being able to like talk out like your behavior with people and like seeing if you can like kind of have counseling. They see a better improvement on their mood, and that could just be that. It's, you can measure it. You know that there has been a change. The question and the answer can be measured. So 2, all right, we saw it happen once. We've seen it happen. Now we got to see this happen multiple times. We need to collect some data. So now that we have like some more background information, and sometimes like you're not going to be collecting like the raw data yourself. You might actually just already get recycle data that's been collected by someone else, but it's like from a reputable source. Like you're gonna get it from let's say National Geographic. You're gonna get it from the National Weather Service. Collect data yourself, or use from a reputable source. This is very important. There's been like sometimes where people try to like they come up with a theory, or they try to take a study like, hey, like if you take like this lemon water drop, you'll lose like 50 pounds like in one day. And the data says it's only happened to one person, and that one person also had like an amputation, which is why they lost like 50 pounds. That that data is not very, not coming from a very reputable source. It's not a very good, the data doesn't really correlate too much to the theory, so that would just throw the whole theory under the bus. The next one is to form a hypothesis. Okay, question versus hypothesis. The question is, the question, whereas the hypothesis is might be the answer. What you think is the answer. And here's the beauty about having a hypothesis. You actually learn more from it being wrong. Kind of like when if you're trying to get from point A to point B and you don't know how to get there, so you just start going in random directions. Well, you find out that this is not the right direction. You find out that this one's not the right direction, nor is this one. Excuse me. Let's get some better lighting. Nor is this one, but then you get confirmation that this is the correct path. Then this actually helps you. It still gets you closer to knowledge. I mean, yes, it is frustrating when you're going through theory, you're thinking something out, and like you hit a dead end, but the dead end just tells you it's not there, it's somewhere else. Turn on some extra light. There we go. So the fourth step is that we need to test this theory. So you need to test hypothesis. And you're like, okay, what's the difference between hypothesis versus theory? So hypothesis can just be like any old, whatever you think it could be, versus a theory has been maybe like a little more, it's a little more fleshed out versus hypothesis. Like the theory of relativity, it's not just someone who made it up, it's kind of been tested through time. So theory is a hypothesis that has been tested. And I do want to mention, we've had theories that are wrong. I mean, people used to believe that all diseases were caused by breathing by bad air, but now we're finding out that disease can be spread through infection, through contaminated water, by not washing your hands. So things change as we get more data, as we observe things, and as we test things, and that's just the beauty of sharing knowledge. That's why we've been able to see a lot more scientific advances, like in cures and a lot of things, kind of like with big data. Also like when, not just for like marketing and like Facebook and YouTube and everyone else giving you like super specific ads, like you were just talking about like buying a watch, and now you have like 30 ads on YouTube and Facebook saying, hey, buy this watch. No, it's more of the sense of like sharing all this knowledge and using it together to like kind of make better theories. So finally, we're going to draw a conclusion. Which is, was the hypothesis correct or not? Okay, all right, we've explained the scientific method. We kind of like see it right now. Let's do an example. Use wonder if I should get another piece of paper to make space or not. I think I should. I will. So I'm just gonna write this out. And we're still talking about the scientific method. So I'm just gonna title this page example. So, researchers observed unusual plant and algae growth in a pond. Yes, you might get scenarios, but trust me, it's much better than like looking at math examples. They sampled the water and also discovered very high concentrations of bacteria. Significant increases in the growth of plants, algae, and bacteria in ponds are often caused by an abundance of phosphates and nitrates. So like phosphates, we know that phosphorus is in it, and nitrates, we know that there's nitrogen in it, along with the other eights. We'll be getting that into the chemistry portion. It's in the water. The pond was fairly close to neighboring farmland. And two streams carried water from the farm to the pond. Okay, I know this looks a little long, but with the exam, it might actually show an experiment, and this is what I wrote. I wrote out the entire experiment, and it might ask you to either write like a multiple choice, select and it'll ask you a question after giving you the experiment and ask you a question about it, or it might actually have you write a short response about it. We'll be getting into the short responses in a moment. We just want to go ahead and identify right now what would be a good hypothesis about the growth in the pond. I do want to mention, maybe you're not so sure about phosphates, nitrates, you're not very good in horticulture, which is like botany, which is about the study of plants. But you don't have to be an expert in all those areas. Beautiful thing about science, unlike with math, is that you can kind of like feel your way around it. Math is like very structured, very linear. You don't know one thing and you're like, it's going to be very difficult to like figure out the rest of the problem. With science, there's a lot of background, there's a lot of overlap, and that is just the beauty of science. So let's read this again. Researchers observed unusual plant and algae growth in pond. Okay, that's the situation. So that is what they saw. They sampled the water and also discovered very high concentrations of bacteria. That's their data. They also saw that there is significant increases in the growth of plants, algae, and bacteria when there's I misspelled often, I'm sorry about that. So what they saw was that there's more phosphates, or like an excess, like extra phosphates and extra nitrates. And it kind of like correlates or suggests at the very least that where there's more phosphates and there's more nitrates, we're going to see more growth of plants, algae, and bacteria. Okay. Wow. Summed it up in the green, everything that I was saying in the pink. The pond was fairly close to neighboring farmland, and 2 streams carried water from the farm to the pond. Okay, so we know that water flows in one direction. So if we have, so the pond was close to neighboring farmland, and 2 streams carried water from the farm to the pond. Okay, so we have a little pond, and there's 2 little streams. So there's 2 little streams. Stream 1, excuse me. Sorry about that. And now we have stream 2. Yeah, it really helps to draw. I know that really applies in math, applies as well in science. And we're saying that the pond was kind of close to like neighboring farmland. So like over here is like, this is the neighboring farmland. Okay, those are supposed to be like the crops, like for the dirt, and they put the little crops in there. So we can assume that all of this phosphates and nitrates might have come from the farmland, kind of like gone downstream. Like the stream would have carried the water down into the pond, and now with all of those extra phosphates and nitrates, now there's like a big increase in plants, algae, and bacteria. Have you guys ever gone to like those ponds, or you want to go swimming and like the water's really green and like everything's really luscious, but you can't see if there's anything like in the bottom where everything's like really slimy? Ew. Yeah, that's exactly this is exactly the kind of picture this example is trying to paint. So a good hypothesis, well, we kind of have a hypothesis written out. Let's kind of say it out in words. Let's use a different color. Let's use purple. Runoff, and that's basically like water that has like run off, like it flowed down. Runoff from the neighboring farmland may be carrying excessive, and by excessive here they mean like an abundance, because sometimes excessive might mean like too much candy. So maybe carrying excessive phosphates and nitrates from fertilizers into the pond. And yes, those of you who do know a little bit more about like fertilizer, like phosphates and nitrates, those are compounds known to be in fertilizer. So it's like, okay, like, well, I don't know, like the phosphate and nitrate came from the farmland. It occurs in fertilizer, and this is a hypothesis. Like, this could just be this could be wrong for all we know. In fact, it could turn out that the farmland has a different stream, and the farmer has like a better setup for like recycling like the phosphates and nitrates. That way all of that fertilizer stays on his farmland instead of being wasted in a pond. Like, there's so many other things, like what ifs, that we're not entirely sure. That's why we go ahead and test the hypothesis. You could add extra fertilizer into the farmland, see if we end up seeing an effect over here. We could decrease the amount of fertilizer, see if there's an effect over here in the pond. This is the very, very, very important thing with scientific method. Just because these two things go together does not mean it is the cause. So let me write this out. So we have cause and effect. The cause comes first, and it causes the effect. All right. However, there may be different things that occur simultaneously, as in things that are happening at the same time. Causation, there's a rule in science, is not correlation. So a causation, a correct cause of something is the ground gets wet. So let's say we know that the ground was wet. We have an effect. And we're trying to determine if something is the cause or it's a correlation. So a cause would be that it's raining. All right, rain falls on the ground, it makes the ground wet. However, a correlation is something that happens at the same time. At the same time, but does not cause it. Correlation would be if there's lightning or thunder. Lightning is not going to make the ground wet. Lightning is electricity flowing, not water. Thunder is a sound that has, yes, thunder you might hear when there's a thunderstorm or when it's raining, but it's not going to make the ground wet. So this is a sound, and this is electricity. Here we're talking about water, and over here we're talking about water. Okay, so these two match up. Okay, this is the cause, this is the effect. This is very extremely important when you're making debates, when you're arguing with someone. Like, let's say you're trying to figure out, oh, this is actually a very important skill for car crashes. When there's a car accident, they're trying to find out, okay, so like, what was the sequence of events? What happened first? It could be that someone looked at their phone while they were driving, and then it caused the accident to happen, and then the person hit their head, and then it caused a rollover and it caused another accident. But if we take those things out of order, we need to find out what was the root cause. That way you could find out like whose fault it was in the car accident. Okay, so we've been talking about what's the cause and what's the effect. So this is called, the cause is called the independent variable. Whereas the effect is called a dependent variable. Okay, you may be saying, Miss, both of them have the word variable, both of them have the word dependent. What does that mean? Okay, let's try to like backtrack. Independent means you don't need nobody. Same thing with the cause. The cause doesn't really care. Like, it just exists. Whereas the dependent variable is much like a child. It depends on their parent. So it needs the cause to exist. So, just like how if it's raining. It's raining. The rain doesn't even care about like the ground getting wet and everything. It's just raining. But the ground's not going to get wet unless rain falls on it. There we go. So we have rain is the independent variable. So that's the thing that can like happen or not happen. That's why it's called variable. Variable means like yes or no if it is happening or not. So if it rains, then the ground will get wet. So if it rains, then the ground will get wet. Ta-da! And it's also just likewise very, very important kind of seeing in what situations, what are the independent and what are the dependent variables. This is very much also very important in your own personal lives. Like you may seek to ask yourself, what is something that is like on its own independent variable? For example, the independent variable could be like someone having acne, or excuse me. Okay, so like if we're talking about acne, you might just have like acne on your face. It exists. And then you have, now you're going to be seeing, you know what, I want to find out which one of these two medications or face washes improve my acne's appearance. So the dependent variable, or like what your face might look like afterwards, is going to depend on what we put on. Okay, so now we're going to kind of introduce another word called a control. So this is very important when we're doing experiments. We have the independent variable, the dependent variable, and then the control. It's not really a variable, it's just going to be considered the constant. So we have basically three scenarios. So with the control variable, you want to make sure everything stays the same. You can't really start changing like a bunch of things and you're not so sure what would have been the alternative. That's why in pharmaceutical, which is like when they're making like medications, pharmaceutical trials, there's a control group. It's called the placebo. It's just seeing like what would be the normal progression of the disease without treatment. That way you can really do a comparison. For example, you might there might be an example of someone doing an ointment for like a muscle relaxer and saying like, okay, like, so people who have like have had a strain or a sprain, then we're going to put this medication on and we're going to see if this improves. Well, how are we going to know if it improves if we don't know what's the alternative? So there are going to be some people who we're just going to monitor who are hurt and we're not going to do anything for them. That's incredibly cruel, yes. And this is kind of like told when people are in a pharmaceutical study that they might be part of the control. It'll probably just be like a fake medication. So we need to see like, okay, so we see in the control group people who have like a sprained, a strain or like a torn muscle. We see that they heal like in a week. Now we saw that when we put in like our new medication, our new ointment, like the company's trying to develop, we see that people heal in 2 days. So from 7 days on just the person healing in 7 days on their own or healing in 2 days, yes, it makes sense to continue making this product because it's actually helping people. And that's how you kind of use your control to see like, is it really worth it? Is it really doing something? Is it being effective? It's your comparison. You're going to always compare back to your control. And I will be very honest with you, sometimes when you're doing experiments and you're following the scientific method, you actually might find out that what you're developing, your hypothesis, actually doesn't result in that much of a difference. Like let's say, again with the strained muscle, if it was 7 days and this one healed like in 6 days, it's not really too much worth it. Like it's not much of a difference. And that's what happens with a lot of these medications. They're sometimes not as effective and like they don't become as popular, or it's kind of like, all right, that's kind of like money down the drain in research. Now we need to go ahead and just make our research better. And it's only when scientists, researchers, and like everyone in those businesses realize, all right, we need to do better, we need to improve. That way we can make something that's totally better. Okay, so going back to our independent and dependent variable, so the dependent variable is the phenomenon you're studying. Phenomenon or phenomena. Because you're looking at the effect, remember. So like, we observe something, what we're actually seeing is the effect, and that's what we're studying, the phenomenon. Whereas the independent variable is like our hypothesis. Of what is affecting the dependent variable. Okay, so let's go through an example. I know this is like a lot of like terminology, a lot of like embedded little examples thrown in. So let's talk an example with a little plant. Little plant. Okay. So we're doing a study on a plant and we want to see if like a certain amount of like whether I should use sugar water or whether I should use like a certain juice to see like if the plant's gonna grow. So my independent variables could be right here, like my the liquid I use. So like I could use like plain water to like water the plant. I could then use either like juice, like sugar water, and I could use like different concentrations of sugar water, like 5% sugar, 10% sugar. I could even like try like using Coke or soda or pop, as it's say in the Midwestern United States. And then like what I'm gonna be observing, what's gonna be the dependent thing, what's gonna like, if I do this, then this will happen. I might see how tall the plant grows, like how much it grows. So like effects I'm gonna see afterward are gonna be the height of the plant. Maybe it's general health. Maybe like the number of leaves I see. So like health go into like how luscious the plant looks. And now like we have, remember, the control here. Actually, let me put a double line. Like further emphasize the difference. So with the control, we're gonna keep one where it's like the same. And we're gonna make sure that there's only one thing that's going on different between these different experiments. So like maybe I might use plain water, sugar water, and soda. So I might have 3 plants going under that experiment. I gotta have one as a control. I gotta make sure that if the liquid is the part that I'm testing, I gotta make sure the soil is the same. I gotta make sure I'm testing the same kind of plant. Like I'm not gonna be testing an oak plant, comparing it to a pumpkin and then a carrot. Like it's got to be like the same, you know, like you can't compare apples to oranges. You got to compare apples to apples, oranges to oranges. Same thing with the control. You got to make sure everything else is the same or as like as same as possible. So like with here, for this example, we kind of like maybe keep everything else constant, like plant type, soil for plant, this is where you might actually begin to see errors and like studies that happen is where they don't have a good control. Like maybe they end up saying like, hey, like the soda is actually very great for plants. Go ahead and put soda in your plants. And like we saw that there was actually like the plants were getting bigger, but then you find out that they didn't actually do a good control, and the plants that were getting soda, by coincidence, correlation, not causation, had better soil than the ones that had plain water. So then you find out, oh look, the control is off, the whole experiment is off, the whole theory is off, you gotta redo it again. Important thing of scientific theory, right here. Alright, we covered quite a bit of ground. Yeah, alright, so we're gonna like cut this off for today, and we're gonna be talking about different parts of like sample, population, experiments, and just getting on more into like the scientific information. Alright, see you tomorrow.